Okay, so we're halfway through trying to do our Riemann integral step by step. Kind of this is what we did. We're in this together, and we are now on to the lower limit. So get yourself a cup of tea, make sure you're comfortable, and let's jump right in.
So, we've already done our upper limit. We've got our function is x plus 3dx. We're going between 2 and 4. We know our partitions. They're 2 plus 2k over n. And we know the general gist of what's happening. We've got all of these different little partitions, and we're going to add up the sum of those rectangles created by our partitions. So, looking at the lower limit, so we're just going to call this L, lower limit, of our function with these partitions. Remembering again, what we're doing is finding the sum of all the area of these rectangles, except now we're doing a kind of underestimation. So we're going to have the sum as k is running from 1 all the way up to n, and in this case we're looking at, actually it's this kind of diagram here. In this case, we're looking at the function on the left-hand side, so that's going to be f of, totally spat there, wonderful, f of xk minus 1, and that's going to be multiplied by xk minus 1. Now where that comes from is f of xk minus 1, that's the length of this line, and xk minus 1, that's going to be the length of this line here. And that's how we do the area of a rectangle, length times breadth. So let's do our actual substitutions and see where that ends up. Put this in here, because this is the information that we need. So that's going to be equal to the sum of k is equal to 1 all the way up to n, f of xk minus 1. So that means we take what xk minus 1 is and we substitute that into our function. So what would xk minus 1 be? Well, it's going to be this 2 plus 2k minus 1 over n, and remember to multiply those brackets out, so that's essentially going to become 2k minus 2. And then what does the f function do, f of x? Well, that adds 3 on. So overall, we are left with 2 plus 2k minus 2 over n plus 3. Close down brackets over. Now we need to work out what xk minus 1 would be. Did we do that last time? Have we already done that? Oh yeah, look, there it is, right there. We don't even need to work that out. So, last time we went through all of our xk minus 1, and it turned out to be 2 over n. That was really nice. I like that. I like what you have done with that function. Oof, that's going to save us a bit of time. So, let's see what we can do with this bit up here. Tidy it up. We're going to have equal to the sum of, because got to have that start of every line, k equal to 1, running up to n. This I'm going to put first because it's got kind of variables and stuff. So that's going to be 2k minus 2 over n. And the constant terms, the 2 and the 3, I'm going to lump those together into what is known as 5. And I'm going to put that second because it's a constant. Close those brackets over. We're going to multiply that by 2 over n. Okay, let's actually do the multiplication. Time to multiply. We're going to have, whoop, where's my pink pen to show what's going on here? This one times by that one over there. Boop. So that's going to be sum of k is equal to 1, running all the way up to n. 2 lots of this. Should I leave it factorized form or should I properly multiply it out? I'm going to factorize that and make that 4k minus 1 over n. Why not? And that's that multiplied, is it? N squared, there we go. That's me multiplied the top of this and the bottom of this, and then now I need to multiply the 5 by 2 over n, which is going to give me plus 10 over n. Wunderbar. Now, because we've got the sum of these two things here, which I'll put in brackets because we're doing the sum of both of these, what I can do is I can put the sum on either side. Rather than doing some of these, I can do some of this and then some of this. Some of this and some of that. So I'm going to get sum from k equals 1 up to n of 4 k minus 1 all over n squared plus sum k equals 1 all the way up to n of 10 over n. And now, making it even easier for myself, rather than doing the sum of these, I can take the constants out. Let's take the constant out. And because the only variable going on is k, then I can actually take out 4 over n squared. Is that a good plan? Yeah, I can do that. So we're going to have 4 over n squared of k equals 1 all the way up to n, k minus 1. We might have to do something with that in a second to make it even easier. It's like these Riemann integrals just do themselves. Plus, now this is all constant, so that's going to be 10 over n, take that out as my constant, sum of k equals 1 all the way up to n of 1. Right, let's do like we did up here, where we split the sum up, but with this thing here. So I'm going to have like the sum of k and also take away the sum of 1. So that's going to be 4 over n squared times the sum of k equals 1 all the way up to n minus, still need my constant, 4 over n squared, the sum of k is equal to 1 all the way up to n of 1, plus, different constant now, 10 over n, same sum, k is equal to 1 all the way up to n. I should just have a stamp for that, of 1. Excellent. Let's see where this goes. You're missing a k. There we go. 4 over n squared, sum of k minus 4 over n squared, sum of 1, plus 10 over n, sum of 1. Okay, now actually getting rid of all of these sum signs. Remember, pink pen, this one here, the sum of k, as k runs from 1 all the way up to n, that really means 1 plus 2 plus 3 plus 4 plus blah 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 all the way up to n. And because of Gauss, we know a good formula for that. So let's start with our constant, 4 over n squared. Thank you, Gauss. We're going to have n plus 1 over 2. Now that is a formula for the sum of, so for example, say you only wanted to know the sum of all the numbers up to 4, like 1 plus 2 plus 3 plus 4. You would do 4 times 4 plus 1 over 2, which is 4 times 5, which is 20, over 2, which is 10. And let's just have a look. 4 plus 3 is 7, plus 2 is 9, plus 1 is 10. There we go, Gauss works. Which is not exactly a proof, but oh well. And then this one here, since it's just 1 and it's running all the way up to n, it's just going to work out to be n. So we're going to get minus 4 n over n squared, which we'll tidy up in a second, plus, same thing going over here, you're going to get 10 n over n. Okay, let's see what we can cancel out and what's going to happen when we times these things together. So, remember that these are getting multiplied together, but we can do some cancelling to start off with straight away. The 4 and the 2, they're going to cancel down just to leave a 2 on the top. That's dividing both of them by 2. The n and the n squared, well, it's going to get rid of the n and it's going to get rid of the squared. dividing both of those by n. So that's going to leave me with an n on the bottom. And there's nothing that matches up with this n plus 1, so that's just going to be there, n plus 1. This one over here, I've got an n on the top and an n squared on the bottom. So again, I can get rid of the squared. I'm still going to have 4, and I'm going to have n on the bottom. And I like this one. Boop, boop. Goodbye. We're going to have plus 10. Okay, does that tidy up any better? I don't think so. I'm quite happy with how it is. 2 n plus 1 over n, take away 4n plus 10. And that's how we find our lower limits. Yay!
So thanks for watching these kind of, I guess less entertaining, but more mathematical, so overall more entertaining videos about how to do the lower limit and the upper limit for the Riemann sums that we did in one of my previous videos. If you want more of this kind of like longer form, low-key video where it's just me kind of going through my maths thoughts, then let me know, and I'll see you next time. Have fun!